let's do one more example of optimization here. Right? So in this case, we're doing a bit more of a geometric problem. Right? So we want to say we have this parabola here, and we want to find the point on the parabola, the spot on the parabola, which is closest to the point 1, 4. Right? So this could be something like, let's say you're, on a racetrack or something, and you want to know at what point on the racetrack you're closest to, I don't know, some camera on a pole or something. Right? It's that kind of idea. Right? So, what would this look like here? Let's go ahead and graph this parabola. Right? Since this parabola is y squared equals 2x, it's going to open to the right here. 1, 2, 3, 4. Bit of 2 down here. Let me put a 2 here. There's the y direction and the x direction. 1, 2. Right, so this might not be perfectly to scale, but the idea is still there. Right? So our parabola looks something like this. Right? And then our point 1, 4 is up here somewhere. So what we're looking for is, well, what point on the blue parabola here is closest to this point? Right? So how do we measure that distance? Well, we're sort of trying to measure the lengths of these lines here, right? Which one of those pink lines is the shortest? Right, let me re-emphasize the dot there. Right? So what is our objective function in this case? So we need to figure out a way to build that. And really, we're finding a distance here. Right? So like, let's say for this one here, here's a distance. What I'm going to do is just leave this point on the parabola here as an unspecified xy. So what I'm going to make my objective function here is just, I want to minimize the distance function from any point to 1, 4. So my objective is going to be distance from x, y to 1, 4. Right? So that would be, well, distance formula. So x minus 1 squared plus y minus 4 squared, and then square root all of that. Right? That's the distance function. Now, all right, well, let's see. We got a bit of a messy function here, but maybe we'll plug in the constraint and good things will happen. Right? So what should our constraint be here? Well, for a constraint, right now for our objective function, all we've said is it's the distance from xy to 1, 4. We've not said anything about where xy has to be. Right? We want our point to be on this parabola, so our constraint is just, well, the parabola. Right? We want our point to stay on that parabola, so that's our constraint. Okay? It's what we're restricted to. All right, so let's see what happens to the objective function. Right, so d will become, let's see, we can solve this for x to give 1/2 y squared. Okay. So we get 1/2 y squared minus 1 squared plus y minus 4 All right. So, we can, if we want, FOIL these things out and try and simplify, but that square root isn't actually going anywhere. So there's a neat trick here. And because this objective function is always positive, what we know then is that, well, since that's always positive, then if we square it, whatever the minimum of this function is will also be the minimum of the squared function, right? Because again, this function is never negative. So when we square it, we can't turn any negative numbers positive. So the smallest number of this is going to be a positive number, which means if we square it, well, the smallest thing there is still going to be positive. So let's say the better objective function is, let's call it f, which is going to be the square of d, right? Which in this case is 1/2 y squared minus 1 squared plus y minus 4 squared. Right? But we could still FOIL all this stuff out, and I still actually recommend not doing that. Reason being is this derivative will look a lot nicer if we just leave it like this. Or it'll be a lot easier to do. Just do the chain rule. Okay, so we're going to work with this as our objective function now. Again, notice that, well, here there's no restriction at all on the y value, right? Because this graph here exists for the whole, for all values of y, there's a spot of this parabola above it. There's no breaks or jumps anywhere, so there's no reason to really cut this off. Right? So all y values are fine here. All right, so we're going to take our derivative, so f prime. Using the chain rule, we get this as 2 times 1/2 y squared minus 1 times the derivative of the inside there, which is just y, plus 2 times y minus 4. Derivative of this inside is 1, so we're just here. And let's see, so what are we going to get at the end of the day here? We're going to get y cubed. Yeah, let's just multiply this out. Minus 2y plus 2y minus 8. Right? So this is just y cubed minus 8 equals 0. Right? Sorry, I didn't mean to set it equal to 0 just yet. Right, so that's our derivative. And now we want to find critical numbers. And again, this expression here is never undefined. So, all right, we'll just set it equal to 0. And this turns out to say that y has to equal 2. So this is the only critical number. Since that's the only critical number, all we need to do is verify whether it's a local minimum or not, right? That's our goal. Now, if you remember from the last video, we talked about this first derivative test here. All right, we can use that. The neat thing here is the second derivative test also will apply, right? Because the second derivative test, being positive or negative, is going to tell us these things right here. As long as we only have one critical number, we're all good to go. So let's do this with the second derivative because it'll be a bit quicker. Right, so f double prime is 3y squared. And so f double prime of 2 is going to be 12, which is positive, right? So y equals 2 is a minimum. Well, really an absolute minimum, right? And that's what we wanted. We wanted to minimize the distance from this point to this blue curve. And it turns out that, well, the one to do that is this one right here. That's the smallest line I can draw from 1, 4 to the parabola. Okay. So we want to summarize our answer here. So let's see. Since y squared equals 2x, we want to solve for x here. So this is 4 equals 2x, x equals 2. So to summarize our answer, the point on y squared equals 2x closest to 1, 4 is x is 2, y is 2, so 2, 2. And that's it. That's all there is to it, right? So these problems, you know, it's okay to kind of like choose an easier objective function to work with or a better one. You still want to set it up this way so you know what you're working with. But again, as long as this function is always positive, or at the very least, always greater than or equal to 0. I forgot to put that in there. This is greater than or equal to 0. As long as it's non-negative, when we square it, it remains non-negative. And again, the important part of that is, you know, any maximum you have is going to be preserved. Any minimum you have is going to be preserved, right? The max and mins of the locations, the y values, not the output. But the critical numbers are going to be the same. And, you know, the critical numbers, if it's a local minimum here for f, it's going to be a local minimum for d. The local maximum for f, it's going to be a local maximum for d as well, right? Yeah, so that's another nice trick we have with optimization. All right.